Okay, example 6. Up to this point, our instructions have been verify that the equation is an identity. So basically, they are saying, here's an identity, prove it. Now, on example 6, we are being given some equations that may or may not be identities, and we need to figure out whether they are or not. Okay, there's a couple of different ways to do this. We can do these the same way we did the other problems. Or we can plug in a value for theta and see if we get the same value on each side. Okay, let's go ahead and give this a try, see if we can get the sides to match. We might get to a point where there's no way to make them match, and then we'll know that it's false, perhaps. So let's see what happens. We're going to start with the right-hand side and start with a common denominator and distribute. So right now our denominator is cosine theta, so we want this 1 to be cosine theta over cosine theta. And then that's plus 2 times our stuff up here. Let's go ahead and distribute that 2 through. So 2 sine cubed theta minus 2 sine theta over cosine theta. Alright, so that gives us, simplified, we have cosine theta. I'm just adding everything all the way across. And I'm going to change the order a little bit. Is that what this is having me do? We're actually going to factor something out right here, which is weird because we just multiplied the 2 in there. Well, now we're going to factor the 2 back out with some other stuff as well. To begin with, I'm just going to go ahead and reverse the order that this stuff is in. So I'm going to create these and you'll see why in just a second. 2 sine theta plus 2 sine cubed theta. That whole thing is over cosine theta. So now this part right here, let's focus on it. We're going to take negative 2 sine theta factored out of this. So negative 2 sine theta factored out of negative 2 sine theta is positive 1. And then negative 2 sine theta factored out of positive 2 sine cubed theta is negative sine squared theta. You kind of have to just look ahead at things and how they can happen. So I don't know if you recognize this now. That is a Pythagorean identity, and that is cosine squared. So we now have this nice little Pythagorean substitution. Okay, let's rewrite what we've got. So we have cosine theta minus 2 sine theta times 1 minus sine squared theta, which turns into cosine squared theta all over cosine. Okay, so now everything has a cosine in it, but let's factor it out first so we don't forget to reduce it both places. So I'm going to factor out my cosine here, so that leaves me with 1, and factor out one of these cosines. So we're left with 2 sine theta cosine theta over cosine theta. And then those cancel. And we have this pretty little thing. I don't know if that helps us. Let's see where we should go from here. Okay, at this point we've really got to think outside the box, because usually we take sine squared plus cosine squared and replace it with 1. We don't very often go the other direction, but that is exactly what we need to do in this case. So we're going to take this 1 right here. I tried to change the color, it didn't cooperate. We're going to take that 1 right there, and we're going to do a Pythagorean substitution again. only this time the 1 is going to be replaced by sine squared plus cosine squared. Okay, so let's write that out. Let me change the thickness of my tan again. So we end up with sine squared theta plus cosine squared theta instead of that 1, and then minus 2 sine theta cosine theta. We got rid of our fraction. It reduced, right? So that at least is nice. Okay, I'm going to put this in a slightly different order. If I do this in this order, sine squared theta minus 2 sine theta cosine theta plus cosine squared theta. I don't know if you recognize this the way it is, but think of it this way. Think of it as like x squared minus 2xy plus y squared. I don't know if that helped. We did this kind of thing when we were completing the square, because this is a perfect square trinomial. Does that help? Square trinomial. And what that means is it factors into x minus y squared. Okay, because that's kind of what we did when we did our completing the square stuff, right? We wanted it to factor so that we had that x minus h, x minus or y minus k stuff, right? So this right here will factor into sine squared theta minus cosine squared theta twice. I'm going to write it out just to make sure we see what's happening. Okay, and that, of course, can be written as sine. It shouldn't be squared, should it? I made a mistake. You guys are probably watching me and like cringing. No, not squared. It's gone. Maybe nobody noticed. Glad I noticed. Okay, so we're taking that out. So then altogether, this is sine theta minus cosine theta squared, which is proved. That's our left-hand side right here. Okay, let's look at this a slightly different way. I already have this written up, so it won't take very long to explain. A lot of you were in class and saw this already. So another option is to choose a value for theta to plug in. We should avoid 45 degrees because sine and cosine would both be the same number, and that can mess things up. And we should avoid 90 degree or 180 degree reference angles because ones and zeros can sometimes wreak havoc with actually proving it. So something weird like 30 or 60 degrees, or pi 6, pi thirds, or something even weirder. But why go weirder? Let's keep it simple. So I'm going to substitute 30 degrees in everywhere where we have a theta. So starting, we're going to do it separately on each side. So on the left-hand side, plug it in. That gives us sine of 30 is 1/2, cosine of 30 is square root of 3 over 2. We subtract those. We square this thing right here. So that combine our fractions together. Square it out. I think I just multiplied that binomial together, so there's my perfect square trinomial there from doing that. Combine the 1 and the 3 together. I feel like I missed a step here somewhere, because 1 plus 3 is 4, so we should have 4 minus 2 square root 3 over 4, and then if we throw that in a calculator, it's approximately equal to 0.13397, blah, blah, blah. The reason we get that decimal is you'll see over here we don't get the same answer. We could tweak it to make it look like this, but it's easier to just verify it with a decimal to show that both answers are the same. Alright, so over here on the right hand side we have 1 plus 2 times the sine of 30 cubed minus the sine of 30 all over the cosine of 30. So sine of 30 is 1/2, so we'll cube that. Sine of 30 is 1/2 again, subtract that. Cosine of 30 is square root of 3 over 2. simplify this thing so we can see that work here. 1/2 cubed is 1/8, and then 1/8 minus 1/2 is the same thing as 1/8 minus 4/8, which is -3/8, and then we do our copy dot flip to get rid of the fractions in the fraction, so we multiply by the reciprocal of square root of 3 over 2, so 2 over square root of 3, and we multiply that together, and we get, I kind of skipped a step here because here's -6 and 8 square root of 3, but then it divides out by 2, so it reduces to this, and then we end up multiplying by that 2 again, so we get that 6 again. It wouldn't have mattered if you reduced this or not. It would have been just fine to get the same decimal if we'd left it like this. Just, I don't know if you can see that, how it reduced. Okay, so we have 1 plus 2 times this ugly fraction thing. And that means it's 1 minus, because 2 times -3 over 4 square root 3. At this point, I didn't want to try and make this look like this, so I threw it in a calculator, and I get the same decimal I got over here, which more or less verifies that this identity could be true, because both sides are equal, at least for 30 degrees. I could try it again with 60 or another angle if I wanted to, or even something random and use a calculator to get decimals and check it that way.